All right. So in this case, I want us to check the applications now of our complex numbers as we managed to have the introduction. So make sure that you go through that and understand how the complex numbers can be simplified. So they were given calculating values of a series RLC circuit using complex notation. As we saw that we can use the simple notation before, on the same circuit that we are given here, we apply this before using the simple notation. So for complex numbers, you'll be given use complex notation to calculate the following 1.1, the total impedance. All right, so as we saw that when I introduced, I talked about the RLC circuit. So this one, let us just, as we are answering this question, shall be adding some notes since this is an example. As you be presenting a series RLC circuit, because this is the major part actually that you are going to have in your syllabus. Okay, you're not gonna like work with RL alone or RC alone. The major part will be RLC. Yes, you can have the RL in those normal or basic calculations, which is fine. I say the impedance can be given Z, which is equal to R plus J, the difference between XL and XC. Okay, I talked about that on the introduction, that this is how our Z is going to be given. So as you calculate your XL and XC, then you'll see which one is bigger there, then you can, okay, obtain your Z. So as you can see, we need XL and we need XC. The resistance is already there. This, we are not given reactances. You are given the value of the inductor, the value of the capacitor. Sometimes they give you the reactances. It's an advantage when it is like that. But in this case, guys, we are not given. All right. So that's so it's going to be 1.1. So let us just have our XL. So as you can see, we need XL 2 pi FL, meaning to say XL is going to be 2 pi times the frequency, which is 50 times L, the inductance value, which is 0.15. So that was going to give us the value of XL, which is 47.124. Okay, ohms, just leave it like that. You're going to see that simplification later on. Then the XC, you do the same thing. As we can see, as we saw that XC is 1 over 2 pi FC. So that is going to be 1 over 2 pi times the frequency, which is 50 times C, the capacitance value, which is 100 times 10 to the exponent of -6, 100 microfarad. So that was going to give us the value of XC, which is 31.831 ohms. So having the value of XC and having the value of XL, these values that we are seeing, they will help us now to determine our Z. As we are saying, Z is equal to, that's we've got R there, the resistance value. So we've got R from our diagram, the resistance is 25. So that's 25 plus J, XL minus XC. Our XL is given as what? 47.124 minus XC. Our XC, which is 31.831, like this. So as you are simplifying, that is going to give us the value of Z, which is 25. Subtract these two values, that was going to be a positive. So it's positive J. In this case, you're going to obtain 15.293. That's a positive. So you've got the total impedance of the circuit in ohms. So guys, this part is important. Just have your excellent. You have the Z, total impedance of the circuit. But as we calculated this, it is written in rectangular form. And like I said, it is best that you must have in both formats because you do not know what's going to happen in simplification. So the same Z can be written in polar form. You don't need to go back to your mathematical calculation. Like I said on the introduction, you can use your calculator now. Introduction to complex numbers. Just have the what? Calculator. Converting to what? To polar form. We need to polar form this time. So I said it's shift polar form, that's a plus. Then you're going to separate this, that's 25. To separate this to 15, it's going to be shift closed bracket. So that's 15, 293. Then close the bracket, you've got the answer there. Remember, in polar form, you expect to have r angle of theta. So thus, we are going to be given the value of r, 29.305. So this 65, so it's going to change into a 7. So that's going to be 29.307. Then the angle is also given theta. You move on aside here. I get your theta, 31.45, and the 9 is going to change this into a 5. So that was going to be 31.455 degrees as your total impedance of the whole circuit. So you're going to have this in polar form also. Because the simplification, you do not know what's going to happen there. Okay, so you need to have both formats. Okay, let's move on to number 1.2. Sorry, that's 1.2, the total current. So as we can see, there's a voltage, and we calculated the total impedance of everything there. So we are simply going to divide. So the total current is supposed to be given as, that's 1.2. You are supposed to have your total current as the total voltage over the total impedance. But this voltage is going to be affected by a certain angle. The voltage will be affected by a certain angle. That is what you need to understand there. Okay, why? Let me put it this way before we talk of the simplification of the theta. Why am I talking of this? Remember, this is a division. And when I talked of division, I said division is best that you do it what? In a polar form. Division, it's best in polar form. That's, we have to write this in what? In polar form. So the question is, are we having the voltage in polar form? The voltage, the total voltage, remember, this is a series RLC circuit where the voltage is in phase. The total voltage is going to be at what? At 0 degrees. Total, this is, remember when you're presenting your phasor diagram, the total voltage was here, then you can present your XL and your XC, then the result, and that is, but you're having that VT there in phase with the resistance at what? At 0 degrees. So you're going to see that whenever the voltage, they're not going to write the angle, you must know that it must be at 0 degrees. So that's 100 at an angle of 0 degrees divided to the total impedance in polar form. That's why you have to write this in rectangular and polar form. So for division, it's best in polar form. You're going to take the one in polar form, this one, not the rectangular one, in polar form, this one. Okay, so that is what you're going to have there. So taking this in polar form, as we saw, that was 29.307. Then the angle was 31.455. Why is it that it is best to simplify in polar form? We can now get back to the introduction now, where I say division, you divide the numbers here separately. So you're going to divide that. You're going to obtain 3.412. What about the angles? The angles here, you subtract. Subtract, division, you subtract. So it's theta 1 minus theta 2 on the angles, you subtract. So meaning to say, the angle that you're supposed to have obtained, it was supposed to be 0 minus 31.455, which was going to give us minus 31.455 degrees. That is what you're supposed to have. We have got this as our total current in amperes. Current measured in amperes. That's it. Then the voltage drop on 1.3 on each component, meaning to say across the resistor, inductor, capacitor. Remember, we are in a series circuit where this total current is the same throughout. Remember, a series circuit. So to have VR, we're going to have current times the resistance value, current times inductive reactance, capacitive reactance. So we have got the total current, guys. So this is what we're going to have. on these reactances now, you are supposed to be very, very careful on these reactances. You're supposed now to be very, very careful. Remember when I referred about when I referred on the introduction there to say a part that you have got a purely inductive, the part of the inductive part, this one of the inductive part, this one. The XL that we are seeing here as 47.124 is taken at an angle of 90 degrees. So this is 47.124 at an angle of positive. It will be at a positive 90 degrees inductor. They're purely inductive on its own like that. The same thing on the capacitive, but it will be a negative now. So meaning to say this one is going to be taken as it is XC 31.831 at an angle of what? Minus 90 degrees now. So this is how actually our angles are going to be. Okay? Inductive plus 90, capacitive minus 9. The resistance, like I said, it's in phase with the voltage. So it will be at 0 degrees, this one. It will be 25 at an angle of 0 degrees because VR is in phase, this R there. So it's going to be the same, that R is in phase with what? The VT. So that means if it is at 0, the same thing with our VT, that's at what? At 0 degrees. So you must understand all these, that the capacitor, how is it presented, this and that. All right. So this is it. So with this information, guys, we're going to calculate the voltage drop. Remember, I said the current is the same. So let's calculate the voltage drop on each component, okay? I'm just going to write our total current here so that we do not keep on revisiting our total current. Remember, it was 3,412 at an angle of minus 31.455 degrees, which is this one. That was our total current here. All right. So we're going to have each component. Okay, that's 1.3. So 1.3, let's start with the resistor. So the voltage across the resistor, that is supposed to be current across the resistor times the resistance value. But because of the angles that we are seeing, the current that is across the resistor is having the angle. Remember, this is equal to current across the resistor, current across the inductor, current across the capacitor, because it's a series circuit. So that's, you're going to use the total current in place of that total, in place of the current across the what? The resistor. You use the total current as it is. Okay, so that's 3,412 at an angle of what? Minus 31.455 degrees. Multiply to the resistance value. The resistance is 25 at an angle of what? Of 0 degrees. As I explained before, it's in phase with the total voltage. So where are we, guys? We are back to the polar form. Multiplication. You see, we are back. As long as you're dealing multiplication, it's easier because you multiply the numbers on their own. Remember I said, maybe R1 times R2, at the angles you add theta 1 plus theta 2. So that's going to multiply this to 25. Just like that. So 3.142 times 25. Thus we are obtaining, in this case, we're going to obtain 85.3. And the angles you add theta 1 plus theta 2. So you add minus 31.445 plus this 0. So that is going to give us negative 31.455 degrees. That's the voltage across the resistor, having an angle there. So since we're not going to use any other calculations there, so there's no need for us to convert this to rectangular form. As you can see, guys, there's no other calculations, just the phasor diagram. So just leave it like that. So we move on to another component, okay, across the inductor. So the voltage across the inductor, was supposed to be the current across the inductor times XL, being given in polar form with an angle theta, angle theta. So our IL is equal to IT because it's series. So you're going to use IT there, which is 3,412 at an angle of minus 31.455 degrees. So this is our current, total current times the reactance across the inductor. Remember, I said this is taken as a purely inductive, so it's at plus 90. So that's 47.124 at an angle of a positive 90 degrees. So that was going to give you the VL, just like what we had on the previous case. You multiply the numbers together. So that was going to give us something like 160,787. What about the angles? You add. So it's supposed to be negative 31.455 plus 90 degrees. Okay, so what are you going to have in that case? That was going to give us positive. Remember, this is polar form, so you indicate the angle. So it was going to be positive 58,545 degrees like this. Okay, that's our VL. The voltage across the inductor. What do we need? Across the capacitor, the last one, each component, all right? So let's move on to the capacitor. The voltage across the capacitor, which is VC. So again, it was supposed to be IC times XC at an angle theta, at an angle theta. IC is the same as the total current. So that's going to be 3,412 at an angle of minus 31,455. Remember your format. XC for a purely capacitive, it will be at negative 90 degrees. So that's, you're going to take that as it is at a negative 90 degrees. So that was 31,831 at an angle of minus 90 degrees. So that is going to give us the value across the what? Across the capacitor, the voltage. So again, multiply the numbers on their own. That was going to give us 108,607. The angles you add, minus 31.455, you add to minus 90 like that. So it is going to give us minus 121,455 degrees. Okay, that's the voltage across the capacitor. We have calculated all voltages. And the question that is following now is to have the phasor diagram on 1.2. Draw the phasor diagram. All right. So on the phasor diagram, remember we are talking of a series RLC circuit, guys. For a series RLC circuit, we saw this, that our phasor diagram, when we worked with a simple circuit, when we're dealing with the simple notation, I'm going to explain two ways here. Okay, let me just choose this one. So that's for the phasor diagram. All right. So as we saw previously on a simple circuit, that we are actually dealing with two components, inductor and capacitor at the same time, affected to the resistor. So definitely using impedance or using the reactances, using impedance. When working with the impedance, the total impedance that we are seeing here, this total impedance that we are seeing, where is it? In polar form, this one, in polar form. The total impedance that we are seeing can be used to tell us what is exactly happening. Remember your simplification. I'm saying using impedances. So it's supposed to be like this. So remember, when using impedance, you're going to have the total impedance, whether it's this side or it's going to be this side, which is being given by the angle. Remember, on the introduction, I said positive, you go in the anti-clockwise. So mean you say the Z is at 31.45 degrees, just before 90 degrees. So we're going to have something like this, okay, representing our Z. So that is equal to, the value is 29, the value is 29,307 ohms, separated by the angle of 31. We are going in the anti-clockwise because the positive, 31,455 degrees. Okay, I talked about this on the introduction, angles, positive anti-clockwise. So at 0 degrees, that is where we have the resistance and the total voltage. Remember, I said resistance at 0 degrees in phase with the total voltage. So that's we are going to indicate the total voltage here. But our resistance is what? The resistance value is 25 there. So that is 25. And the voltage you're given, this was 100 volts. The voltage that you're given, the total voltage. But this is not just on the impedance, because the impedance is affected from the reactances XL and XC, which are taken XL at positive 90. Remember, your XL is straight here. So you're going to indicate your XL straight, positive 90 degrees. So this is 47,124 ohms. Your XC direct going down there in the negative 90 degrees. That is 31.831 ohms. That's our XC. So that's we have got our phasor diagram using the impedances. So from this, we are going to note that if it is that we are using the impedance, this is what you're going to note. We saw that definitely VT and R are in phase. Thus, at what? At 0 degrees. This one is directly at 0 degrees. So Z, okay. Another part is that the Z that we are seeing is affected by the angle. Is affected by the angle. The Z that we are seeing there is affected by the angle. So meaning to say, if our Z is given as R theta like this, and it's a positive, being positive, remember, when you're presenting XL, it's positive 90. It's positive 90 degrees X. So just being positive, it means our circuit is more, or it is mainly inductive. It favors the inductive side. It is more inductive. That's why we see even this Z is on top where the inductor is on XL there. That is where it is. Having a positive. A negative in this angle, a negative in this angle, if it is given as minus R theta like that, and being negative, this one, just being negative, it shows that our circuit is mainly, or it is more capacitive. Mainly capacitive. It favors the capacitor side where XC is. So you're going to present this side. That is where a negative is going to be in that region. That is what we can tell from Z. The angle is important. If it was a negative there, you are not going to present your Z on top. You're going to present your Z going down there. Okay? Another thing to note is between these two, the XL and XC. Always, as we can see, this is at positive 90. This is at negative 90 degrees. So definitely we are going to see they are separated by a straight line. They are on a straight line. XL and XC will be on a straight line, separated by what? By 90 degrees. So we're going to see that XL and XC are separated by 180 degrees in between. That's a straight line. That's a straight line. So if your XL and XC are not on a straight line, guys, it means it's a wrong presentation. They are supposed to be straight, 90 and minus 90. What did we use to present this? From the impedance. So this is what I want you to note. You can present your phasor diagram from there. All right. But this is not only the part that we have, guys. The phasor diagram, remember, they asked you to calculate these voltages. They asked you to calculate these voltages. So meaning to say the phasor diagram can also be presented from voltages. We can present our phasor diagram from voltages. So what is the difference? Okay, now see a little bit part which is just, that's not even that much, guys. All right, so still on number 2. So this is going to be another way using voltages, because we are given that the voltage is already there. You're still on the phasor diagram. So we could have us answer this using what? Using voltages. So when using voltages, this is what I want you to be very, very careful with in your simplification. You are going to notice that the total voltage, that is not going to change, guys. The total voltage is, like I said, is at what? At 0 degrees. You must consider each angle as given. Consider each angle as given. Consider each angle properly, guys, in terms of the direction. You're going to be having voltage of each part. But knowing that our VT is in phase with it, that one is not going to change. VT is in phase. VT is in phase with what? With the resistance. Meaning to say they will be at what? At 0 degrees. Any other part, you must use the voltage as it is given. I mean the angle as it is given. As we saw previously, what happened between XL and XC, it was that XL is direct at 90 degrees. XC was direct at minus 90 degrees going down. So straight vertically going down. And this forms a straight line. It is going to be the same thing on the voltages. The only difference is that they are no longer at 90 degrees like this to say they are going to form a straight vertical line like this. But VT, but this, for the inductor, let's say VL, and for the capacitor, let's say VC. They are going to be on a straight line, but not a vertical one like this one, because this one, it's when this is 90 and when this is minus 90. But they maintain the same concept that they are on a straight line. This VL, whenever you present, once you just present VL to say, okay, you can see the angle of VL. Let's say VL is it's at an angle of 30 degrees like this. This is where our VL is. The moment you present your VL, guys, do not waste your time. Extend that line going the other way like that. If VL is this side, VC will be on the other side, meaning to say it is going to take the rest of this other angle that we're going to be given from the origin. This one, from the origin, your VC is going to be taken like this. This one, the whole of this angle that is remaining here as a negative, because remember the direction, negative. That's a negative angle that we'll be having. Where the difference between these two, it gives us 180 between VL and VC on a straight line. You must get 180 degrees. So thus, in this case, this is a straight line, 180 degrees, form a straight line. So you must test that before any presentation. If you're using voltages, test that if you're getting 180 degrees. So according to our question, we are going to test VL is here. I'm going to test our angles. VL, the angle there is 58,545. This is our the angle there. Focus with the angle because we need the angle to get 180. What is the angle here? It's minus 121. The minus is for the direction, but as you take the angle, you just take it as it is, as 121 like that. So if you add 121 as it is like this, 121,455 like this, you are going to obtain 180 degrees. This is to confirm this part that I'm explaining. It's supposed to give us a straight line. All right, so I think, guys, this is enough for us to present our phasor diagram. So this is what I'm going to need. Since we have to consider the voltages of each there, just going to have, let me just try to have broken lines. Let's just hope, guys, I'm going to win. See, these software, sometimes they just misbehave, but let us just hope we're going to win. All right, and it's not the one that I want. Actually, okay, let me just use the broken line. Let me just use the broken line. So because we do not know exactly where our points are, so I'm just going to use the broken line to indicate like the normal part that we understand, like a horizontal line. It means we are at 0 degrees. So it's like 0 degrees, 90 degrees, 180 degrees, 27. We know that that concept is the one that you're going to follow there. All right. So let's start with the voltage. VT in phase with what? Resistance at 0 degrees, the total voltage. So we can present that at 0 degrees. The total voltage is 100. So at 0 degrees, guys, it simply means this is going to be straight in this line. Okay, just take this one. It's going to be straight like that. Okay, sorry for that. Sorry for that. Let's just hope, guys, it's not going to affect us here. Straight like this in the horizontal. In this horizontal, that's at 0 degrees. We have the 0 degrees there. So this is where we are going to present our total voltage, VT, which was 100 volts. And as you know, it's in phase with the resistance. Just write R there. Do not write the value. It's not even important. Okay. We move on to the VC and the VL. We say these two, they're in a straight line. So just indicate one. By indicating one, you're indicating another one. Okay. We saw that we even proved VL and VC. So VL, the angle there is 58. So you can just target VL because the angle is positive. 58.545. Which direction are we going? Anti-clockwise. So maybe the angle is somewhere there. Just before what? 90 degrees. You indicate. So as you are indicating this, you're supposed to have it like this, guys. You're supposed to have a straight line like this. But as you are indicating that straight line, continue with it. Continue with it as you are indicating it. Because these two, they lie on the same line. VL, if VL was positive going this one, this was our VL, this angle that I'm indicating here. This is your VL, positive 58 anti-clockwise, which is what? 58,545 degrees. The angle being what? I mean, the resultant of VL, 160, we tried the value of the voltage there. So that was our VL, 160,787 volts. You've got the voltage there. As you are indicating this voltage this side of VL, VC will be on the opposite direction on a straight line. That is the idea. So meaning to say, this other hand, we are having our VC. What is the value of our VC? 108. So that's 108,607 volts. And the angle is minus 120. This one, the angle that we are seeing, guys, is the one that is remaining. Remember, negative, we are going in the anti-clockwise. Is the one that we are actually from what? We are taking your angles. Your angles, they are measured from zero, from the origin. From the origin. So moving from the origin here, from the origin, going this direction here to this point, that is the angle that is presented there, which is 121. Okay, let me just write it inside like this, 121,455 degrees. The angle that's between here, between this point and here, that is the one that we are seeing. But in between, from here to here, guys, this is a straight line. So that is the 180. So if you add these two angles, what are you getting? 180. If you add these two angles, you must get 180. This angle plus this angle. So we have VL and VC. Okay. Let's go back to the last one, which is the VR, the voltage across the resistor, this one. So if you were to take a consideration, you are going to see that the voltage across the resistor is in phase with the total current. Remember your total current here. Same angle, minus 31.455, minus 31, same angle, VR and IT. Like what we had on the resistance, the angle on the resistance and the angle on the VT. So we are going to notice in every situation when it is like this, in every situation, VR is in phase with what? The total current, which is IR, because remember, in series, IR is equal to IT, which is that total current. So instead of us writing IR, we're just going to write IT, so that we're not going to have a problem. But that IR, that IT there is our current across the resistor. Okay, they're in phase. So what is the angle? They mean they're honest. They're not like opposite direct, guys. It's same angle, same direction, not opposite like what we saw between VL and the VC to say the other one is the other way. No, this one they'll be on the same line. If it is going this way, they'll be on the same line. VR and this current across the what? Across the resistor, which is the total current. They'll be on the same line, same direction. Same direction, but those ones, they're in phase, the VL and the VC, opposite, phase and opposite to each other. They'll be opposite. So we have got VR, guys. You can present it. VR is what? The angle there, minus 31, which is same as what we saw on IT, minus 31. So minus 31, remember I said on the introduction, a negative angle is the one that we take when we are measuring in a normal clockwise direction. So negative 31, you're going to just make an assumption from 0 to 90. Maybe negative 31 is somewhere in between there. You're just going to make an assumption of that part that you are going to have. Okay, so let me just assume mine to be somewhere there. Let's say my negative 31 is somewhere there. Okay, so let's say this is where my angle was here, from this point, from the horizontal to this line. That is the angle, but you don't write it as a negative, just write the angle as it is. Okay, 31,455 degrees. So thus we have got what? VR in that case. That's our VR, which is 85,3. So that's 85,3. The value there is 85,3. But as we saw that they are in the same line with the total current, so we're going also to indicate that total current, okay, because they're in phase, total current or IR, which is 3.412. So you also indicate that. So that's your total current or the current across the resistor. Okay, the current across the what? The resistor or the total current or whatever that you want to write. So that total current or the current across the resistor was 3.412 amps. In the same line with the VR, same as what is happening, resistance of 25 that you are given with the voltage at 0 degrees. They must be in the same line. So this is our phasor diagram using what? Voltages. using voltages. So as you are to revise, it is up to you. Which simplification are you going to opt for? Are you going to opt for the first one, where we had of the impedances, or for the voltages? So no matter the way, guys, even if you do not want to learn this, one way or the other, they will give you a question that will need you to present this. So you go back to this situation and present. You consider each angle that you're given there. How the angle is given. Positive, anti-clockwise, negative, clockwise. VL, VC form 180 degrees. VR and IT or IR are in the same direction, in the same phase. So that's it. Let us just continue to revise as much questions as we can as we are revising for the exams that are ahead of time till we meet again.